Hello, this is a second video about a new three-dimensional soil model in FEM-Design. This new three-dimensional soil model, which includes the nonlinear material model for soil, is available from version 15. So now I will show you some very small practical example about the nonlinear soil calculation in FEM-Design. I will not show you how to build a model and how to put and adjust the input parameters. I will show you the model, then we will evaluate the results of the calculated results. Then I will show you what can we calculate in FEM-Design with this new 3D geomodel, and I will show you some comparison between the analytical solution and between the numerical solution, what FEM-Design produced during the nonlinear soil calculation. So let's start with a very simple example. So I will show you first a very easy example about a slab, a foundation slab, and I will show you what's the difference between the bedding modulus and between three-dimensional soil calculation. So first of all, let's see a simple plate. So here you can see a plate, a 20 centimeter thick plate with a bedding modulus under of it, and I apply uniform distributed load at the top of this slab. So as we know that if I check the displacement according to this load, you can see here we have constant displacement on both nodes of this foundation slab. So it's because we have just uniform load at the top of the slab, and we just apply a constant bedding modulus under the slab, we get the same settlement in every point of the slab. Therefore, if we check the bending moment of the slab, the bending moment will show us that the mx and the my value, the different bending moment in the different direction, are equally zero in every point. So you can see here in a color palette view that we have zero bending moment, mx value or my value or mxy value. So every direction we have zero bending moments or torsional moments in the slab according to this modeling situation. But if we have this foundation slab on a soil block, you can see here a soil block under the slab. We applied the foundation slab on the top of this soil, and I also applied a distributed load on this slab. And of course, if I check the different layers of this soil block, you can see here the soil analytical model here, and of course if I check the supporting system of the soil, you can see that we have different type of supporting direction around the slab. So you can check here the soil support, and you can see here at the side walls we have just support in the perpendicular direction of this side wall, and at the bottom of this soil block we have just vertical support. So you can see here the supports of the soil block, and we apply just the slab on the top of this soil. So the connection between the top of the soil and between the foundation slab is continuous. So we have a continuous connection between the slab nodes and between the soil nodes at the top of the soil. We can check the three-dimensional mesh. You can see the three-dimensional mesh under the slab. So we have some refinement around the slab here, and if we check in this case the results with just a linear soil calculation, you can see here that the settlement profile under the slab is not constant. So you can see here that the former result what we get with the what we get with the bedding modulus solution. The bedding modulus solution gives us just a constant settlement of the slab, but now if we check the settlement profile of this plate, this will show us that the settlement profile is not constant at all, because in this case, if I check the settlements here, we get not just 0 settlements, we get different settlements here. So we have at the middle point of the slab it's 5.7 millimeter, and at the edges we have less settlement, it's almost 3 millimeters. And of course, if I check the internal forces in the slab, we have just not a constant distribution of bending moments in mx and in y direction also, and of course we have torsional moments in the slab in this case. So this was just not a nonlinear soil calculation, but it was a three-dimensional soil calculation in this case. So it means that these differences comes from not just from the different material properties, it's come from the 3D soil behavior. So if we use the bedding modulus in a most simple way, we can get quite different results when we use the more accurate modeling method with the three-dimensional solid elements. So it was a very simple example. So let's see just a bit bigger and more detailed example about the 3D soil building interaction. So I open a bigger file with a regular building with the different stories, and then I will show you the different calculation method based on the linear calculation and based on the nonlinear calculation. So you can see here a building with 4 floors here, and we have just different type of foundation. You can see here isolated foundation, wall foundation here, and the slab foundation slab here, and we modeled under the building a complete soil block. So this will be our nonlinear soil block calculation model. So you can see here under the building the different types of 3D soil mesh, and at the top of the building we use beams, shells, and so on and so on, and we apply some wind load and self weight of the soil at the top of the structure. And of course, for the nonlinear calculation we apply not just the structural dead load, then a soil dead load in a specific load case. Okay, so we run this analysis in 2 different ways. The first combination contains just the linear calculation of the building. So the first combination will be the linear calculation of the building, and you can see here that the maximum displacement, the maximum displacement vector is 111 millimeters. So this load combination contains the same load cases, but the first one was run with the linear calculation with 3D soil, and the second one was calculated with the nonlinear material properties, considering the nonlinear material properties. So you can see here the maximum settlement in 127 millimeter in this case. So we have a bit larger settlement, larger settlement here, because with the nonlinear material properties we consider the plasticity in the soil under the structure. So let's check the soil material properties. So here we just apply one soil layer, and I can check the soil properties here. So you can see that in this case we applied a drained analysis. So we applied a 5 kPa cohesion and 30 degrees of phi characteristic phi value. So the friction angle is 30 degrees and the cohesion was 5 kPa in this case, and the Young's modulus of the soil is about 7,000 kPa, and the Poisson's ratio is 0.3. And we consider by the calculation the nonlinear behavior of the soil. So here we can check at the table that here at the second load combination we apply the nonlinear soil calculation. So this is checked in. But there is a quite different cases in the load combination. I said earlier that it's the same, the results will the same, but by the nonlinear load combination we need to apply the load case which one includes the soil self-weight. So you can see here in the first load combination we do not apply the soil self-weight here because we would like to check just the settlement from the external loads and from the structural loads, and we do not want to see the settlements of the soil according to its self-weight. But in second case, the second load combination was calculated with a nonlinear soil calculation. So here I need to apply the self-weight in the load into this load combination, because with this soil self-weight we calculated the initial stress state of the soil, and these initial stress state affect the final results based on the nonlinear soil calculation. But in the final results with this second load combination, at the end of the calculation the FEM-Design automatically subtract and neglect the settlement from the soil self-weight. So the final results will be according to the external load and the structural load, so the other load cases which one was included in this load combination. So this load case just involved because we need to set the initial stress state of the soil before the other loads consideration during the calculation. So we saw that we have larger settlement because we consider the plasticity in the soil in this case. So what can I do now? I would like to maybe check the plastic points in the soil. So in this case you can see here a new option in this display result window. You can see here a soil plastic condition. So this option is just available for the second load combination because the first load combination was a linear combination, so there are no plastic points in that load combination. So I can check the soil plastic points, the plastic points of the soil in the second load combination, and you can see here with the red dots those integration points which are in plastic condition during the calculation. So you can see here that under the foundations we have several integration points which reached the plastic condition during the calculation and during the external loads. But it not means that it doesn't mean that the soil loses its stability or we reach the we reach load bearing capacity of the foundation, because there are no compound slip surface around the building. So those points are in plastic condition. We have plastic deformation under those foundations. That's why we get larger displacement, larger settlements under larger settlement if we consider the nonlinear behavior of the soil by the settlements. Okay, so let's continue. So it was a complete soil structure interaction with the larger building. So let's get back let's back for some load bearing capacity calculation. What I saw you in the former, what we saw in the former video, what I made. But I just show you the PPT about the calculation background. So now I just would like to show the model in real life. So this one is just a slice of a soil block, and I apply here on the left side a symmetry plane, and I just model the half of the shallow foundation, a wall foundation here, and I apply a uniform load on this shallow foundation, and then I increase the load at the top of this this shallow with this wall foundation. Then I ran a nonlinear soil calculation, and this nonlinear soil calculation included the external load, this uniform load at the top of that wall foundation, and it includes the self-weight of the soil. So first of all, in the first phase of the calculation, we set the initial stress test according to the self-weight of the soil. Then in the second step, we increasing the loads, and then we check the complete Moore-Coulomb behavior and check the plastic strain in the soil. So let's see the results. So you can see here the results in a downscale result. So if I apply, you can see here that it's the scale factor for the displacement is 0.08, so it's a downscaled figure. If I increase the scale, you can see that we have a very strange result here. Next to the wall foundation, we have a volume increasing, a large volume increasing in the soil next to the foundation slab, next to the wall foundation. So it means that these points under the slabs is in plastic conditions. So you can see here that somewhere here, if I make an animation about this displacement figure, you can see that the rest and almost all of the soil has zero displacement, but around the slab there is a slip surface somewhere here, and based on this amount of certain load level, I can check this amount of load level. So the load level in this case, what was applied, is 12 kPa. So it means that we have 1100 millimeter settlement under the slab, and the complete width of the slab was 2 meters. So it means that this slab is reached the load bearing capacity according to the Moore-Coulomb criteria. And I can also check the soil plastic point by this load combination. You can see here under the wall foundation we have the plastic points. So let's compare the results, the settlement profile based on the linear calculation, and just compare it with the former one. So in this case, with the linear calculation, according to the external load, we have just 11 millimeter settlements, and the displacement profile is quite different than with the displacement profile with the nonlinear soil calculation. So this one is just a linear calculation based on the same external load, but with the, if I check the load combination, what was set for the nonlinear soil calculation, we can see here a completely different displacement profile, and it happens because we consider the nonlinearity of the soil. So we can see here that the slip surface occurs under the foundation, and in this case we can calculate the load bearing capacity according to the Moore-Coulomb criteria in FEM-Design. So let's see another example. This one is also the former example was a cohesive soil. Then I will show you frictional soil. So in this case, I just modeled a circular foundation, and I just modeled just a quarter of this foundation, and I use symmetry plane here and on the other side also. So this is the model, and then I also just apply some load at the top of the foundation. So the load in this case, it was 500 kilonewton per square meter, and the load combination is 1 for the soil slab weight, and the factor for this external load is also 1. So then we run a nonlinear soil calculation according to the Moore-Coulomb criteria. So it is a cohesive soil, so the friction angle was about 30 degrees, and the cohesion was just 1 kPa or something like that. So if I check the maximum displacement according to this external load, we can see here a large nodal displacement. So it's a downscaled displacement field. Also, you can see here also a volume increasing around the foundation. It was 500,000 millimeters for the settlement. So it means that according to this applied loads, the foundation loses its stability, and in this case we have a very large plastic deformation under the slab, under the foundation, circular foundation. And you can see here also that around the foundation we have the settlements and we have the slip surface somewhere here, but the rest of the soil block it has almost zero displacement, so far from the foundation slab, because around the foundation slab we reach the shear strength of the soil, and we have a compound slip surface under the foundation slab. So let's continue with another small example. So let's see what we have here. So here you can see the verification of the nonlinear and the stress dependent elastic behavior of the soil. So this model is for the over consolidated soil verification. So in this case we applied an over consolidated material properties for this soil, and we have several parameters here. So we describe this curve where we have the pre-consolidation pressure somewhere here, and before the pre-consolidation pressure we have a higher compression modulus, then it drops down, and we have a smaller compression modulus, then it's increased with the increasing of the stresses in the soil. So for this example I neglected the self-weight of the soil, so this behavior is just under this uniform distributed load at the top. So in this case, if I run the nonlinear calculation, just phase 2 will occur, because in this case there are no self-weight of the soil. So I just would like to get the results based on the nonlinear, the stress dependent elastic behavior of the soil. So we have the settlement. The settlement in this case, considering the nonlinear material properties, is 1600 millimeters, so it's more than 1.5 meter in this case. And I can check the linear calculation. So if I check the linear calculation, so I can see here that in the first load case there was the soil dead load, but it was neglected because in this case the self-weight of the soil was 0. But in the second load case there is the external load in this case, you can see here. So if I check just the settlement based on the external load with the linear load case, I can see here that the settlement from the linear calculation was 100 millimeters. So the nonlinear calculation show us a more soft behavior of the soil according to the pre-consolidation pressure and according to the over-consolidated material model in the program. So it was a very simple example for this material behavior in FEM-Design. So let's see here a cantilever wall. So first of all I will show you just a cantilever wall without any anchorage. So here we have just a wall in the soil, and we have different soil different top of the soil on the right side and on the left side. So here I would like to just calculate the bending moment diagram in this wall according to the nonlinear material behavior of the soil. So according to the plasticity, the molecular plasticity of the soil. So let's check first of all the displacement according to the self-weight based on sorry, not the self-weight, according to the self-weight in a linear combination, but not the displacement, then the bending moment in the wall. So if I check the bending moment diagram in the wall according to the linear calculation, you can see here The bending moment diagram is on the left side. It's 21 kilonewton meter per meter, but this one is based on a linear calculation. So this calculation method is not appropriate to calculate the bending moment in this cantilever wall. But if I check the nonlinear calculation, results of the nonlinear calculation in the nonlinear load case, I can check also the shell internal forces, the mx value, and you can see here it's on the opposite side and it's much higher. It's 165 kilonewton meter per meter. And based on the hand calculation, considering the active and the passive earth pressure on the different side of this wall, we have the same results, almost the same results with hand calculation. So in this case, let's check the connection forces next to the wall. And you can see here the resultant also and the distribution of the connections around the wall. And let's see that for surface. Let's just delete the resultant and let's check just the distribution of the connection forces. So you can see here a very strange distribution of the connection forces, but this is the real solution because we have some higher earth pressure on this wall because the rotational point, according to the equilibrium state, is a bit above from the bottom part of the wall, so it will somewhere here. And in this case there will be not just an active earth pressure here and a passive earth pressure here, then the results will be a mixed earth pressure. So somewhere here we'll have an active earth pressure, then here we'll have a passive one, and we have a changing in this active and passive earth pressure distribution somewhere here according to this rotational point. And we can also show the soil plastic condition in this case, and you can see here also some kind of slip surface here, and this slope of the slip surface is 45 degree plus the half of the friction angle. And here this this tangent of this the tangent of this this part of passive earth pressure situation. So the slip surface somewhere here according to the passive earth pressure is 45 minus the half of the friction angle. So it's almost what we have with the hand calculation, but we have a mixed zone here because the rotational point is not at the bottom of this wall, because if the rotation point will be at the bottom point, there won't be any equilibrium stage in this wall. So you can see that with the nonlinear calculation we have a quite different bending moment distribution in the wall, and it means that in this case we cannot able to design that wall and the bending moment of the wall with the linear calculation, because based on the linear calculation the result is not accurate at all, so the result is false. We can do the nonlinear calculation in this case. So if I modify the thickness of the wall, the results will be almost the same. But if I apply an anchorage at the top of this retaining wall, for example, here I solved it with the point-point connection. So at the side wall I use an anchorage point here, and I make a point-point connection of the top of the wall and the right side of the support of the soil surface here. So in this case the thickness of the slab is 20 centimeter, and let's see the moment distribution according to the nonlinear soil calculation. So the moment distribution in this case, the mx value in that wall is 13 and 38. But in this case the thickness of the wall has a much more effect on the final moment distribution if we have this anchorage than if we do not have any anchorage of the top of the wall. So let's see another example where the geometry is the same, but I changed the thickness of the cantilever wall So let's see if I apply not a 20 centimeter thickness, then just here I can check the thickness of the wall is just 5 centimeter. And if I check the bending moment distribution, you can see here a completely different bending moment distribution, because in this case the rigidity of the wall affects the final moment distribution, because in this case, according to the Moore-Coulomb criteria, if I check the active and passive earth pressure field, you can see here in this case the movement according to the rigidity of the wall is not the same. So if I would like to imagine the passive earth pressure, the passive earth pressure occurs under a much more displacement of the wall in this case. So you can see here that at the underside of the wall, so here the downer part of the wall, we have here no passive earth pressure at all, and we have also an active and a mixed zone here, because the rigidity and the displacement of the wall affect the final plastic and active earth pressure distribution. So in this case I can also check the connection forces, and we can see here a quite different connection forces distribution in this case. So you can see here we have a very large encouragement force here in the point-point connection is 20 kilonewton, and we have a quite different connection distribution, which it was caused by the active and the passive earth pressure in this case. So I would like to show you with this example that with an anchorage at the top of the wall, the thickness of the wall has much more effect on the final bending moment distribution in the wall. But if we don't have this anchorage at the top of the wall, we have almost the same bending moment if I increase or reduce the thickness of the wall. So let's continue with a slope stability problem, for example. First of all, let's check verification effect of the water pressure on the side wall of the problem. So now I have just a soil block and the self weight of the soil, and I applied 3 different groundwater levels. So it's groundwater level 1, 2 and 3, and if I check the final results and the reactions at the side walls, I can see that I set different groundwater levels for the same for the different load combination, but the load combinations contains the same load case, just the self weight of the soil. So in this case, if I run the nonlinear calculation and I check the different reaction forces at the wall, I can see here that if I check the automatic min-max value here, I can see here that at the side wall, if I just show the distribution of the forces, not the resultant, I can check here for load level, for groundwater level 1, we have 140 kPa reaction at the side wall. It's based on the effective lateral earth pressure and based on the water pressure. So in the second case was groundwater level 3. So in this case the reactions at the side wall is just 100, and in the third case the reaction is just 75. So in this case, if I check the different groundwater level, I can see here the for groundwater level 1, which was the highest groundwater level in the model. So there is you can see here the different groundwater levels. This one is not groundwater level 2, it's groundwater level 1, this is groundwater level 2, and this is groundwater level 3. So we get the maximum reactions at the side wall if we have the groundwater level at the top of the soil block. So based on the effective lateral earth pressure, and based on the water level, we have the highest earth pressures and the sum of the lateral pressure on this side wall. And if we reduce the groundwater level here, for example, for load combination 2, and if I just apply groundwater level 3, which was at the bottom of the soil block, the earth pressures and the lateral earth pressure and the sum with the water pressure, so the sum of these two effects, the water pressure and the effective lateral earth pressure, reduces because we apply lower and lower groundwater level in this case. So we consider the effective stresses and the effect of the water pressure on the side walls or in the basement walls in the structure. So let's see a slope stability problem. So in this case I apply a slope, so you can see here the geometry, and the slope, the tangent of the slope is 2 to 1, and I apply just the self weight of the slope, and I would like to analyze that it's a stable slope, it's an unstable slope. So I set a drain behavior for this material properties, so it's 3 kPa for the cohesion and 12-degree friction angle. So you can see here the Young's modulus and the Poisson's ratio here, and I calculated the results, and I just would like to analyze that if this slope is stable or unstable according to its self weight. So I run a nonlinear soil calculation. So first of all, let's just check the linear results according to the self weight. So you can see here the linear displacement field according to its self weight. But for the slope stability analysis, it's not an accurate way to calculate it in a nonlinear way. So let's just see the results of the nonlinear soil calculation, and you can see here that according to the Morculum plasticity, there will be a slip surface under the slope, and it means that it loses its stability. We have the slip surface here, so according to its own self weight, this is an unstable slope. We have almost 2 meter displacement at the bottom point of the slope in this case. So we can analyze the slope stability also with the nonlinear soil calculation module. Okay, so let's see what else we have here. Yes, I show you this moment distribution. Yes, and now I would like to show you not just the I just would like to show you a feature with not just connected to exactly with the soil 3D soil module. So is the influence line module in FEM-Design. So here we have a bridge on the top of a solid block. So these part of the model are soil, 3-dimensional soil, and we apply the bridge at the top of the soil with foundation and with the top plate system and so on and with this arch, and we apply a moving load on the top of the soil. So in this case, this calculation was adjusted. This calculation was made with the linear material model. So you can see here the displacement field according to the moving load. So a static load, we can give a pass of the load, and we can give the different number of the load positions. In this case, we set we set almost 30 load position on that pass, and I check the displacement field according to this moving load. So you can see here, and if I go to the results window, I can show you that how the influence line works in this case. So for the moving load, I can check the load influence line, which will show us that how can I check the different influence line in this case. So I just go to the n value, which is the normal force in the beam. So I say OK. So in the program, say that moving load influence line, select the bar. So I would like to just see the influence line of this bar, according to the moving load on this red pass on the top of the bridge deck here. So now the program say that define a point in the selected objects. So I would like to just choose a cross section on this beam. So I click here, and in this case I just would like to see the influence line of this cross section of this beam. So in this case, this influence line figure show us how big is the normal force in this beam, in this specific cross section with this blue dot, when the load is moving on the bridge. So here we have minus 182 kilonewton compression in this cross section if the load are in this position. So when it's moving, the normal force is changing in this bar, in this cross section. So it's a classical influence line in FEM-Design. So I can check also, for example, the moment, so or the shear force in the beam. So let's check the M by moment. So I also need to just apply choose the beam, and I choose the cross section on that beam, and now I see the MY, the bending moment diagram in this beam, if the position of the moving load is different, so it's moving along the path, and in this case, in this cross section, we have a different bending moment values, of course, because we have a moving load on this top of the structure. So it was not connected confidentially to the soil behavior and the soil module. So you can see here that in this case we have a soil and several soil layers under this bridge. So it was just an example to show you how can we use the influence line feature in FEM-Design with the soil calculation method. But especially it's not connected for a nonlinear soil calculation, so it was just a linear calculation of the influence line in this case. So I think this was my last example what I would like to show you, but there is just one very important thing that in my former video I mentioned that you can download a geotechnical module in 3D, and for this new three-dimensional geomodel, there is a theoretical background and verification and validation handbook. It's 124 pages, so you can download from our download page, and you can find here the theoretical background, the detailed, complete theoretical background for the nonlinear soil calculation and for the soil calculation. And in the second part of this document, you can find several validation and verification example where we calculated the different problems with FEM-Design and compared the results with analytical solution. So you can find here a load bearing capacity calculation, a different plasticity calculation, a different effective lateral pressure and water pressure calculation on side walls and on basement walls, and you can find here several benchmark problems and benchmark calculation and verification and validation calculation of the different main features what we can do with the FEM-Design new 3D model. So if you would like to, you can check these models, you can check these examples, and from the download page you can also download the examples, the FEM-Design files, what I show you in this presentation, and what we modeled and we checked these benchmark problems. So I just made the analytical solution to calculate the bending moment distribution of the mentioned cantilever wall, and also calculated the bending moment diagram, the shear force diagram. We also checked the slope stability problems, so you can see here and find here analytical solutions and other solution which were compared to the FEM-Design calculations. So you can see here and find here the detailed theoretical background of the new 3D soil calculation and lots of verification and validation examples And I repeat myself, you can download the FEM-Design files also next to this documentation from our download page. So thank you for your attention. See you next time.